Welcome to our video on control theory. We will explore the principles of control theory and its applications in vehicles and robots. Control theory studies how to make system outputs follow desired inputs, ensuring predictable and stable behavior. But why is this important in engineering? Control systems are the backbone of modern technology. They enable automated processes, enhance performance, and ensure safety. From the cruise control in cars to sophisticated robotics in factories, control theory is everywhere. Throughout this video, we'll delve into the fundamental principles of control theory, unveil the basic mechanics like feedback loops, and take you through real-world examples. Let's start by understanding what control theory is and why it is crucial in engineering. As we move forward, you'll see how defining the right control strategies makes all the difference in both simple and complex systems. Welcome to our detailed exploration of control theory. Let's dive in by understanding the basic principles of this critical field in engineering. At the heart of control theory lies the concept of feedback loops. These loops adjust inputs based on outputs to achieve desired performance. There are two main types: open-loop systems and closed-loop systems. Open-loop systems operate without any feedback. They work solely based on predefined instructions, making them simpler but often less accurate. Closed-loop systems utilize feedback to consistently adjust their operations, maintaining a higher level of accuracy and stability. Stability and control are key components. A stable system responds predictably to inputs, while a controlled system ensures desired performance over time. Understanding these principles equips you to design systems that are both reliable and effective. From vehicle control systems to robotics, control theory enables innovation and precision. Get ready to explore its fascinating applications. Let's delve into how control theory transforms vehicles into safer, more efficient machines. First, consider cruise control. This system maintains a set speed without constant driver input, using feedback loops to adjust throttle. Next is the anti-lock braking system, ABS. ABS prevents wheels from locking during sudden braking by modulating brake pressure, ensuring that vehicles maintain traction even in slippery conditions. Finally, stability control enhances a vehicle's handling by automatically applying brakes to individual wheels during sharp turns or evasive maneuvers. These examples showcase how crucial control systems are in enhancing vehicle performance and safety. Each system applies core principles of control theory to solve real-world problems. As we move forward, you'll see how similar principles are revolutionizing robotics, paving the way for more innovative applications. In the realm of robotics, control systems are fundamental to achieving sophisticated tasks. Take robotic arms. Control systems enable precise movements essential for assembly and manufacturing. Autonomous navigation is another critical application, guiding robots through complex environments and making real-time decisions. Balancing robots use intricate control algorithms to maintain stability on two wheels or a single leg. Each example shows how control systems transform theoretical principles into practical functionalities. As we delve further, you'll discover the unique challenges that control theory faces in robotics. To grasp these concepts fully, we must first look at specific challenges in control theory. Control theory is not without its challenges. The complexity of systems can be overwhelming, especially with nonlinear dynamics where outputs are not directly proportional to inputs, making behavior unpredictable and difficult to control. Real-time processing adds another layer of difficulty. Systems must make decisions instantaneously, requiring algorithms that operate efficiently under tight time constraints. This need for real-time accuracy demands advanced mathematical and computational tools. Successfully mastering these challenges often determines the effectiveness of a control system. As we delve deeper, we will explore the mathematical foundations key to overcoming these obstacles. To truly understand control theory, a solid grasp of its mathematical foundations is essential. At the heart of this theory are differential equations, Laplace transforms, and state space representation. Differential equations describe how a system evolves over time, providing a dynamic framework for understanding behavior. Laplace transforms simplify the analysis by converting these equations into an easier form to manipulate. State space representation captures the system's state variables and their evolution. Together, these mathematical tools form the bedrock for modeling and analyzing control systems. As we delve deeper into these concepts, remember they are not just abstract ideas, but the backbone of practical applications in vehicles and robotics. Designing control systems is an intricate process that integrates various techniques to ensure optimal performance. Among the most widely used methods are PID controllers, which adjust system inputs to correct errors and meet desired outputs. Optimal control focuses on minimizing a specific cost function, ensuring efficient resource use. Robust control handles uncertainties and maintains performance even when facing unpredictable conditions. Each method brings unique strengths, making them essential tools in control system design. By blending these techniques, engineers can create systems that meet performance criteria and adapt to various conditions. As we continue, we'll see how simulation and testing refine these designs into reliable solutions. Simulation and testing are critical in control system design. Powerful tools like MATLAB and Simulink allow engineers to model and test designs in a virtual environment before physical implementation. These tools dynamically predict how systems will behave under various conditions, significantly reducing deployment risks. In this iterative design process, engineers test different strategies and fine-tune parameters to optimize performance. This approach saves time and resources while enhancing reliability and robustness. Through meticulous simulation and testing, engineers ensure that their designs are theoretically sound and practical. As we move forward, you'll see how robust simulations and rigorous testing protocols lead to successful applications in various industries. As we've journeyed through the principles and intricacies of control theory, it's time to see it in action. Control theory is pivotal in the real world, fundamentally transforming several industries. Consider autonomous vehicles, where control systems ensure safe navigation and decision-making on the move. In industrial automation, control theory optimizes production lines, enhancing efficiency and precision. In aerospace, control systems manage the stability and performance of aircraft and spacecraft. These real-world applications show how theoretical principles translate into impactful solutions. Understanding these applications highlights why control theory is not just academic, but a powerful tool driving innovation across diverse fields. Stay with us as we conclude our exploration and look ahead to the future of control theory. As we conclude our journey through control theory, let's summarize the key points. Control theory is an essential discipline with wide-ranging applications in vehicles and robotics. We've explored systems from cruise control in cars to advanced robotics, relying on principles of feedback loops and stability. The future of control theory is promising, with emerging trends in artificial intelligence and machine learning poised to revolutionize control systems, making them smarter and more adaptive. These advancements will lead to more autonomous vehicles, sophisticated industrial automation, and cutting-edge aerospace technologies. We hope this video has sparked your interest in control theory. Thank you for joining us, and we look forward to seeing your contributions to the future of control systems.